they mention that you could train directly on the baseline instead of training on ensembles? Like training on the softmax on the baseline?
I don't think there is an experiment on it. I don't think there is an experiment on it in this paper, but it has been done. Like if you look at other experiments, other results. In fact, there's a paper that we'll talk about either next time or the time after, which is about distilling from a network into a tree.
Also, the idea is to distill the model that performs best. Right? So you want the best performing model and make it and so compress it into something that can be shipped.
Yeah. So the point of distillation is all about model compression, which actually links back to the original surrogate models in signal theory, which were all about compression. And so this is basically saying, look, I've compressed the big model, and it still does better than the baseline, and it does better than the baseline in a way that is similar to the 10x model, right? So it's 10x reduction in size. You can then see, there's a lot of examples in the wild, they're not in this paper though, of you train one big model and then train a smaller one, and it's almost as good. In fact, I think that's actually what happens with the speech recognition in the Google Assistant when it runs on device. When it runs on device, it's a much smaller model than what you see. Of course, I can't say that for sure because I have nothing to do with it. But because they say it runs on device, I'm pretty sure it's a much smaller model that's been distilled somehow. Also because apparently in 2014, Hinton and the Dean filed a patent for distillation, which just filed a patent application for distillation, which means that they're probably using it commercially. I don't know how valid that's going to be. The application became public 2 weeks ago. It's undecipherable because it's all legal speak, so imagine trying to describe ML in legal speak. It's not for it's not for bedtime reading. But I think that it's actually commercially viable, and it does happen in a while. Yeah.
In this example, did they say the size of the small network?
No, so I think this is.
So that's the speech recognition one.
That's the speech recognition one, right? Yeah. So this is on. It's on a data set that we have no access to, of course. Typical Google style. And this is going on to specialist models.
So if you go up, they up. They say the experiments up top.
Oh yeah.
The architecture's below the equation. If you continue down, stop.
Yeah.
Use an
So
architecture.
this is the architecture of the Compson model. Right, this has 85 million parameters, which 2019 is not a lot, but
Compared to the baseline, it's...
So that is the baseline.
that is the baseline.
Okay, this is the baseline.
Yeah. So yeah, Android voice search, which is why I'm hypothesizing that now they've distilled it, right? Yeah, because it doesn't say, my assumption here is that the distilled single model has the same structure as the baseline, and that the cumbersome model is the ensemble, right? Because otherwise, if this was actually smaller than the baseline, they would have, I would have done that, and I did that actually, but I would have argued strongly that distillation is an effective regularizer. And they don't, so my assumption is that that is not what happened. Okay, so breather, and let's talk about the second paper in this paper. I really think it should have been split in two, and it should have been 10 pages long each, but okay. So now it starts talking about ensembles. So the second concept introduced is an ensemble of specialists. Here they use a data set that has, Google internal data set, 100 million labeled images, 15,000 labels, significantly larger than ImageNet. And the strategy is to try and use distillation, but also to build a model that's effective. So they start with one generalist model, which is trained on all the labels, and then they create specialist models, which are trained on subsets. So call them categories. In ImageNet, these are different sin sets. The interesting thing here, and it's not really that interesting, right? To make a specialized model, you basically select a subset of the classes, and then you use what is called a dustbin class. I love that term. They introduce it with a straight face without giving any explanation. The assumption is, if you train on a whole data set, you have the examples that fit your specialist classes. Everything that isn't in your specialist classes goes into the negative class, right? It's not one of these, so it's the dustbin. Talks about data set, you don't really care, it's an image recognition data set. So the way they then use this for prediction is you run the generalist model, and you pick the top n classes of the generalist model. So the assumption is the generalist model is good enough that it's probably going to have the right class in the top, say, 50, right? You create a set. Then you look at all the specialist models that have an overlap with the set. And you take those, you run all of them, and you basically call it a voting system. There's some details about how they've been aggregated, but I don't think they're important. There's literally millions of ways that lots of ways that you can aggregate different votes on different sets of classes. You have to normalize by the overlap of all the sets of labels that you have in all the specialist models. But then they are looking, so this is performing on inference, and then they look at classification accuracy on this set. So the baseline is the generalist model, and then you add 61 specialist models, and you get a boost. Because none of us are familiar with that data set, we don't know if 43.1 is good. I mean, over 15,000 is definitely not random, so that's, generally speaking, I'm guessing it's okay. Plus 61 specialist models, is that a significant improvement? We don't know. So here it talks about using the soft targets as regularizers. So this is sub-paper 2 of paper 2 in this paper.